Sum and product of roots. Talked a little bit about this earlier in this topic when we were forming quadratic equations and they told us what the roots were. So we've had a bit of a play with this idea. Basically, if we say the two roots are alpha and beta, not actually interested in what they are, more interested in their relationship with the coefficients in the actual equation itself. But it would be true that if I did know what alpha and beta were, I could factorise this quadratic as a outside of x minus alpha, x minus beta. I'll expand the right-hand side out and divide both sides by a, so we can see that relationship a little bit more clearly. And that's where that idea of multiplies together, so there's the two roots, alpha, beta, to give the last number. We can simply say, oh well, if we look at this, then the sum of the roots, so alpha plus beta, will always be minus b on a, and the product of the roots will always be c on a. Okay? So we used it earlier for this sort of equation, or the question I should say. Quadratic equation, roots are 2 and negative 3. So rather than writing it as, well, x minus 2, x plus 3 and expanding the whole thing out, we can simply say, well, hang on, I know the sum of the roots is negative 1, and I know the product of the roots is negative 6, so therefore the equation must have been x squared plus x minus 6. Now in this case, I don't need to go multiply by some constant because it's an equation. And so I could divide by the k, and obviously 0 divided by k is still 0. So I can always make these monic. And if we have ones which are surds, solutions will always appear in conjugate pairs because of the quadratic formula, negative b plus or minus the square root. So we're always going to get that situation where some of the roots, the surds will cancel because one will be plus, one will be minus. Product of the roots, we end up with difference of the two squares, so we end up with an integer as well. And so there it is, x squared minus the sum of the roots plus the product of the roots. So that's one use of this idea that we saw earlier. So if alpha and beta are the roots of this equation, because they ask us simply, what is alpha plus beta? Okay, minus b on a. So for this one, 3 on 2. And what is alpha beta? Well, c on a, so minus a half. Now, they like this question a lot too. The sum of the roots squared. Now, how we do it is, we think of it like this. Well, if I was to get a perfect square, alpha plus beta all squared and expand it out, I would get alpha squared plus 2 alpha beta plus beta squared. Well, if I rearrange that idea, I can say, well, alpha squared plus beta squared then must be the perfect square minus twice alpha beta. So for our question, we've already worked out alpha plus beta and alpha beta, so we just substitute in, and I get an answer of 13 on 4. Now, why do they like this question? Well, once we start thinking about imaginary solutions, if alpha squared plus beta squared turned out to be a negative number, then it's another way of telling that, oh, well, the roots of this equation must be imaginary, because there's no way I could square a real number and come up with a negative answer. Right? So that's why the alpha squared plus beta squared one, we see that idea a lot. Another one they like, reciprocal of the roots. So 1 on alpha plus 1 on beta. The temptation is just to turn alpha plus beta upside down, but of course we can't do that. We've got to turn it into an algebraic fraction, and it becomes alpha plus beta divided by alpha beta. And 3 on 2 over minus a half, so negative 3. So that's another fairly common question. Now, we're going to find the value of m. One root is double the other in x squared plus 6x plus m. All right. So instead of saying the roots are going to be alpha and beta, in this one I'm going to say, well, they're alpha and 2 alpha. So the sum of the roots, alpha plus 2 alpha, would be minus b on a, so in this case minus 6. And the product of the roots would now become alpha times 2 alpha, and I'll get 2 alpha squared is m. Over here I can work out alpha is minus 2, sub it into the other side, and we end up with, there's our value for m, it's 8. If one root is the reciprocal of the other. So again, instead of saying the roots are going to be alpha and beta, I'm going to call them alpha and 1 on alpha. Now, if we're talking about sum of the roots and the product of the roots, one of those becomes really nice, that being the product of the roots. Because if you multiply a number by its reciprocal, you're always going to get 1. So I don't actually need to know what alpha is for this one. I can say, well, alpha times 1 and alpha will be C on A, so 1 on 2m minus 1. And I just got a very simple little equation to solve there. And we get m is 1. Okay, so H is playing with the sum and the product of the roots and their relationship with the coefficients of the equation